Okay guys, in this video we are going to wrap up Focus 2 with a section on adiabatic gas expansions. And so the thing to note about an adiabatic gas expansion is that the heat flow is zero, right? So in this case, the gas, as it expands and does work, it can't absorb, or it doesn't have time to absorb thermal energy from its surroundings. And so as a consequence of that, the change in the internal energy will be equal to the work, and since the gas is expanding and the work is less than zero, the energy of the gas is going to decrease. And this is accompanied by a decrease in the temperature. So for adiabatic gas expansions, the gas expands and does work, it loses energy, and as a consequence of that, its temperature decreases. We can use a couple of adiabatic gas laws. These are actually I call them gas laws in quotes because they're not actually gas laws, but they're like gas laws in the sense that they kind of look like a gas law, but they're modified for adiabatic, in particular, reversible conditions that are listed here. And so you'll see we've got something that looks kind of like Charles' law, except for instead of there being just volume over temperature, it's actually volume to the 1 minus gamma power, where gamma is called the adiabatic coefficient. And it's the ratio of the heat capacities for the gas. It's the heat capacity at constant pressure divided by the heat capacity at constant volume. So here's one that looks kind of like Charles' law, and then you can easily modify this to make it look like Boyle's law as well. Notice that it's pressure times volume to the gamma power. Same thing for the final state of the gas. And so you often have to use one of these two equations when you're solving problems involving an adiabatic reversible gas expansion. Oh, here's just a conceptual slide. It's meant to show that you can think of the adiabatic process as a two-step process. One where the internal energy is held fixed at constant temperature, followed by a cooling of the gas, and you can achieve the same result. So as the adiabatic gas expansion. So this is just, a slide pointing out that you can, that the change in internal energy is a state function, and so you can take a direct path, or you can take a two-step path if you want. This slide shows you the difference between an isotherm, so expansion along an isotherm, where temperature is held constant. So everywhere along this point, you are the temperature has the same value. Compare that to an adiabat curve here, where as the gas expands, the temperature drops. You see that the temperature is, increasing in this diagram, and so the temperature goes down as the gas expands. And so these aren't the same process. Okay, so a reversible isothermal expansion is different from a reversible adiabatic expansion. Namely, the temperature decreases in the adiabatic expansion. So here we have a problem where we're asked to consider an adiabatic reversible gas expansion involving 0.02 moles of argon gas. It's initially at 25 degrees Celsius and 0.05 liters. It then expands to 1 liter. We're given the value of the isochoric heat capacity. They want us to calculate the final temperature of the gas and the work that's being done by the gas during the expansion. So for the final temperature, we're going to need to make use of this this would be non-isobaric Charles Law. Which looks like this. They give us the initial and final volume. they give us part of what we need to calculate gamma. They give us the initial temperature. We need to calculate the final temperature. So I'll just quickly rearrange the equation. This is what we need to evaluate. Gamma, I'll write gamma down here. Gamma is Cp over Cv. For an ideal gas, Cp is going to be Cv plus Nr over Cv. And so we can write that as, well, we can just calculate it. So we'll take the 12.47 joules per Kelvin. We're going to add to that plus 0.020 moles times the gas constant. And then we're going to divide that by that 12.47 joules per Kelvin. So this will give us gamma. I'm getting 1.01. And then what we need to do then is just substitute in the values up here. So we'll have, for the temperature, 298 Kelvin, final volume of 1 liter over 0.05 liters, all of that to the negative 0.01. Notice it's 1 minus gamma. I'm getting 289 Kelvin. So notice the temperature dropped from 298 to 289. So it dropped by 10 degrees. Finally, we're being asked to calculate the work. In this case, the work will be the change in delta U minus the heat. That's 0 for an adiabatic process, so work equals delta U. And delta U for an ideal gas is going to be NCV. Oh, it'll just be CV minus or times the change in temperature, so TF minus TI. So we can calculate that very quickly. 289 minus 298 times 12.47. So I'm getting minus 112 joules. And it would help, of course, if I actually showed you the calculation. Here's the non-isobaric Charles Law. I'm using this to find the final temperature. First, I need to calculate gamma. Gamma is the isobaric heat capacity divided by the isochoric heat capacity. For an ideal gas, Cp is Cv plus Nr. So I plug in all those quantities, I get my gamma of 1.01. Then I take 1 minus 1.01, which gives me this minus 0.01. Calculate the number, I get 289 for the final temperature. To calculate the work, I take delta U minus Q. Q is equal to 0. Delta U is equal to CV times TF minus TI. I just take the temperature difference and multiply by the heat capacity, and I get this value in joules. In this next problem, we're being asked to calculate a final pressure when a sample of argon at 100 kilopascals expands reversibly and adiabatically to twice its volume. What would the final pressure be for an and then they want us to repeat the calculation for an isothermal gas expansion. So let's just focus on the adiabatic reversible expansion first. So we are going to need to use the non-isothermal version of Boyle's law. Okay, it's argon for a monoatomic ideal gas, gamma, Cp over Cv is going to end up being 5/3. And so we know the value of gamma. What we want to do is find the final pressure. So we've got 100 kilopascals for the initial pressure, and then we've got the volume supposedly doubles. All of that is to the 5/3 power. So we'll take 0.5 times 100. And I just want to double check that. 5 divided by 3. I'm getting 31.5 kilopascals for my answer there. They want us to compare that for an isothermal gas expansion. Well, for the isothermal gas expansion, we would just use Boyle's law. And here, we would get 50 kilopascals. Okay, so it's not the same path, right? We have a different final state for the isothermal case compared to the adiabatic reversible case. You also, and this illustrates you can't get away with using isothermal expressions for an adiabatic process. So here we're being asked to do a full set of calculations for an adiabatic reversible gas expansion for a monoatomic ideal gas. We're going from 1 liter to 10 liters. Initially the pressure is at 5 atm, 298 Kelvin. Let's do the adiabatic reversible expansion first. What's the easiest thing to calculate? Q. Q for an adiabatic process is 0. Now, a lot of people want to say delta U and delta H equals 0, but that's not true because the temperature is decreasing. Okay, the temperature is going to drop, and so if you try to use that delta U equals delta H equals 0 stuff for an adiabatic reversible expansion, it's not going to work. You're going to miss half credit for the problem. So what you have to do here in this problem is find the final temperature. Okay, so we're going to have to use this non-isobaric version of Charles' law, solve for the final temperature. All right, we're dealing with a monoatomic ideal gas, so gamma equals 5/3. So we've got 298 Kelvin, final volume 10 liters over 1 liter. That's to the 1 minus 5/3 power. it's helpful just to evaluate that. So 1 minus 5 divided by 3, right? That exponent is minus 0.667. So we'll take 10 to the 0.667, use the minus sign, and then multiply that by 298 Kelvin, and so we get a temperature drop down to 64.2 Kelvin. That's our final temperature. Now we're in a position to calculate work and delta U. Work will equal delta U minus Q, and delta U is going to be equal to 3/2 NR times the temperature difference. So that's delta U. As we said earlier, Q equals 0, so work equals delta U. We're going to need to know the number of moles of gas for this calculation. So N equals pressure times volume over RT. We can choose either the initial state or the final state. I'll just do the initial state. Volume of 1 liter. And then we use this version of the gas constant. And that's at 298 Kelvin. I'm getting 0.2 moles. Now we'll use the 8.314 joules per mole Kelvin. And then our temperature difference, we've got 64.2 minus 298. I'm getting minus 583 joules out of that calculation. Delta H is going to be equal to 5/3 delta U. Minus 972 joules. Now, the reason it's 5/3 is because delta H is equal to, it's going to be equal to 5/2 NR delta T, right? This is CV, and that's CP, the molar versions of it. Okay, notice how they're 5/3, and so I divide delta U by 3 and multiply by 5 to give me the correct formula. So this is for a monoatomic ideal gas. If I had a diatomic ideal gas, I would have been multiplying by 7/5. In part B, this time it's different. We have now an irreversible gas expansion. So that those two formulas at the beginning, these two formulas here, these do not work for the irreversible adiabatic expansion. Nevertheless, we've got another trick up our sleeve. For part B, Q is still equal to 0. But this time, when we go to calculate work, we just fall back on our original definition. Our original ways of calculating work. Work will be minus PEXT times the delta V for this problem. Right? This is PV work against a constant external pressure. So it's minus, we've got 0.500 ATMs Our volume change is 9 liters, and then we'll multiply that by 101.3 joules per liter ATM. So the work is minus 456 joules. We still have the relationship that in this problem, so we'll just use the first law, delta U equals Q plus W. Q equals 0, so delta U equals W, but we also have that delta U equals, I'll write it here, delta U equals CV delta T. We'll write it as NCVM delta T. Okay, and so that's, for this monatomic ideal gas, that's 3/2 NR delta T. So we can use the value of work, which equals delta U, to calculate the final temperature. So why don't we go ahead and do that. And so we'll just write that, okay, we'll just say that work equals 3/2 NR, so we will divide by that 3/2 NR, so we'll have 2/3 times the work divided by NR. That is going to be equal to TF minus TI, so TF will be TI plus 2/3 the work divided by N times R. So we'll take, our TI is 298 Kelvin. We've got the 2/3. The work is minus 456 joules. The number of moles of gas was, I believe, 0.2 moles, and we'll multiply that by 8.314 joules per mole Kelvin. Times 2/3, and then we're going to add to that 298, and so the temperature drops down to 115 Kelvin. So that's our final temperature. So we can then go and calculate delta U. Will be 3/2 times N times R times TF minus TI. I'm getting, well, of course I'm getting minus 456 because that's the same thing. I should have calculated delta H, which is 5/3. So we'll just multiply that by 5, divide by 3, minus 760. Probably 761 joules in this case. So there's the delta H calculation. So with that, I think I'm going to go ahead and stop this video here, and we'll get started with the next focus, which covers the second law and third law of thermodynamics in our next video.